Let us start this video by summarizing what we have learned in the last video. We started with a collection of sets for which length was already known. I have given it a name, script F. This collection was the collection of all the intervals in closed AB. Then, out of these sets, we manufactured lots of other sets by using countably many set operations. That was what we called our Borel sigma field, script B, collection of all sets created by combining members of script F using countable union, intersection and complementation. Now our hope is that since we know the lengths of all these, so we can combine the lengths to get lengths of all members of script B as well uniquely. Is that always possible? That sounds like a very natural thing, but there is a problem that we are going to discuss now with a small toy example. In our toy example, we start with our initial collection, very small, just a finite collection. I have the entire set AB and any two intervals I and j, and I tell you what the lengths of these are. To fix idea, suppose I take A equal to 0 and B equal to 1. In that case, length of this has to be 1. And I tell you that length of this interval is 2 by 3. Length of this is half. Now I shall try to manufacture all possible sets that I can by combining these three using countably many set operations. But since I am only working with finitely many, so countably many set operation is same as finitely many set operation, and it's not difficult to see that the collection of all generated sets would be, of course, I have 0, 1, I have I have j, they are there. Obviously, empty set is also there. I have got I complement, j complement, I intersection j, I union j, I complement intersection j, I complement intersection j, I intersection j complement, then I union j whole complement. Of course, you can also write it as I complement intersection j complement, I intersection j whole complement, and there will be a few more. You can easily convince yourself that there should be 16 such sets, and so far I have counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 4 more are there. But let's continue with our exposition. My question is, if I tell you that I has length 2/3 and j has length half, both of them are lying inside this unit interval, can you find out the length of all these things? In particular, can you find length of I intersection j? Not really, because you know that there are two intervals, you do not know how much they are going to overlap. For instance, this thing j may be completely a subset of I. Or it could be this is I and this is j, in which case this will be the intersection. You have no way of finding out the overlap based on the lengths of the two individual intervals. However, if I tell you this also, the length of I intersection j, then it is pretty obvious that you can work out the length of everything else. So, the initial collection should have this property. Whenever I specify lengths of I and j, I should also tell you how much they overlap. Once I tell you how much they overlap, you can work out the length of the union and the others. So, this set script F should better be closed under intersections. Whenever you specify length of two sets, remember to specify the length for their intersection as well. So, you see, even for this toy example, we need some extra condition on script F. Just because I can manufacture all sets of script B from script F, that does not mean specification of length of elements of script F will immediately give you unique specification of length of elements of script P. We need that extra condition. In this case at least, it turns out to be that the script F should be closed under intersection. That's a sufficient condition. I'm not saying it's a necessary condition. For instance, if I specify this, then also you can work out all the rest. But that is one condition which works in every case. Now what we saw for the toy example with only finitely many things surprisingly actually holds even for an infinite collection, and that is by no means a trivial theorem. That is Caratheodory extension theorem, which has got many different versions. Some of them have nothing to do with Caratheodory, so other mathematicians have created them, and you can manufacture your own versions also by slightly tweaking the conditions. So we start with a non-empty set omega, and script F is that initial collection of subsets of omega for which you are going to specify the length. So in particular you know the length of the entire thing, that's why I said omega is in script F. And whenever you specify the length of two sets, you are also specifying the length of the overlap. So I am writing script F is closed under intersection, finite intersection, that's all that we need. And here is that length function, or in general a measure. So lambda script F to 0 to infinity, that is countable additive. So all that I need for this lambda is any function non-negative and countably additive, which means whenever you have any a1 to an inside this disjoint and their union is in script F, then lambda should split up. So your AIs must be disjoint, they are in script F, and their union is in script F. I am not saying whenever this condition holds, this must also hold. If both the conditions hold, then we have lambda of union AI equals summation lambda ui. So this entire thing is what is meant by countably additive. We also assume that the length of the entire thing is finite. Then this lambda can be extended uniquely to script B, the smallest sigma algebra containing script F, that is script B is as before, all the sets that you can manufacture by combining sets of script F using countable operations. Then extended uniquely means based on only these values, you can uniquely determine the values of lambda for those sets as well. So that is Caratheodory extension theorem, and its main idea, that is closed under finite intersection, the need for that condition can be felt even from the toy example. Now let us see what happens in our case. In our case, this is the collection of all intervals. Now intervals has this interesting property that whenever you take two intervals, their intersection is again an interval. Of course, it could be that one interval is like this, the other is like this, in which case this is empty, but empty set is also in script F because you know the length of empty is 0. So we can use the Caratheodory extension to claim that there is indeed the way to define uniquely the length of all sets in the Borel sigma algebra. Well, in this problem, I am giving you omega 1, 2, 3, 4 and two sets there, 1 and the double term set 2, 3. We are working with probabilities. In place of length, I am working with probability in this case. So the entire set has probability 1, and I also specify the probabilities for these four sets. Well, this you know probability 1, this you know probability 0. For these two, I am specifying 1/4 and half. So that's all that I have specified. I am not saying each one of them has equal probability or anything. I am merely saying this has probability 1/4, this has probability half. From this you have to work out script B, that is set of all collection of all sets that you can manufacture by combining these, and also find out the probabilities for each of the sets in script B.